Thank you so much, Anthony. Now we'll be starting right away. Give Anthony a big round of applause to start with his presentation. Anthony, the stage is yours now.
Thanks very much. Hey, everybody. I'm Anthony. I work at Microsoft. I'm the lead Python advocate at Microsoft. And I do a lot of work in open source, work on CPython and a bunch of other projects. I'm excited to show some stuff that has evolved. Did anyone attend my talk at PyCon APAC last year? Anyone in the room? A couple? Yeah. Okay, cool. I'm going to show you some progress that we've made in the last year on that. We're going to talk a lot about parallelism and concurrency. This is my website. If you want to contact me on Fostodon, like Mastodon instance, I'm also on the thing formerly known as Twitter. And the code samples, the notes from this talk, and also any links to anything I mention are on that QR code. That QR code will also appear at the end of the talk. So if you miss it now, you can scan it later on in the session. Cool. So there's some things, I've listed them as prerequisites. This is slightly tongue-in-cheek, but there's some talks I really recommend you watch to get some more background on some of the stuff we're going to cover today. So make notes of these. They're in the QR code in the corner. Eric Snow gave a great talk on Subinterpreters at PyCon US 2023. Sam Gross gave a keynote on free threading. The initial proposal, which then kind of became accepted and is now in the new release. I recommend watching that talk. He explains how it works, what the idea was, and how it came to fruition. There's a talk on async versus sync in Python at PyCon US. Building a JIT for CPython was mentioned in the last talk. That's a great one to watch. Overcoming the guild with subinterpreters and immutability. I strongly recommend that. I've got a chapter in my book on CPython internals, on parallelism and concurrency, which explains some of these topics in detail. We've only got 30 minutes today, so I'm going to give you like a high-level overview as to how these things work. But if you want some more details, and if you're really, really bored, you can read my master's thesis, which goes into a lot of detail over 78 pages. So let's talk about parallelism and concurrency. So when you have some work to be done, you can split that work up into smaller pieces. And the idea with parallelism is you've got multiple workers which can do the job in parallel. And to illustrate that, okay, so first thing, does everyone recognize this thing here, this toy, a Rubik's Cube? So if it took me, to be honest, it'd probably take me a month to solve a Rubik's Cube. If I got 10 friends and we sat there with the same cube, could we solve it in a tenth of the time? No, because you can't split the problem up. You can't pull it apart and give it to different friends. So instead, I'm going to give you another analogy, which is this one. And I need 3 volunteers that have a pen. So if you're one of the people who has a pen and can draw, then put your hand up. Okay, so I want you to draw a picture of a dog because it would take me, let's say, a minute to draw a picture of a dog, and I need to draw 4 pictures. So I'm going to split this task up, and we're going to do them in parallel, okay? So if you want to draw the dog, put your hand up, and I'll give you a piece of paper. Yeah. 1, 2, 3. Okay, so I'm the main thread, so I have to issue the jobs to the other workers. And whilst I'm doing that, I can't draw, okay? So I'm the main thread. And whilst they're doing that, now I can get on with drawing my dog. Okay. And this is a parallelism problem because I've finished. Some of them are still going. So the jobs are going to finish at different times. But now you need to then deliver that result back to me because I'm the main thread. So I've got my amazing drawing here. Okay. So it's not just that you can take the length of the problem and divide it by the number of workers. It's not really that simple. You have to work out how do you split the problem up, how do you exchange data between the workers, and which is the thread that is coordinating the workers. And this kind of comes down to what we do with parallelism. It's not as simple as just dividing it by the number of CPU cores and saying, okay, that's the time it will take to calculate. So as a recap, in Python, we've got some options for parallel execution. We've got threads, which run in parallel, and there's an asterisk there because there's a massive caveat. The startup time is very small. So when I'm doing my dog analogy, the startup time is the time it takes me to launch a worker, which was the time it took me to walk from here to over there and deliver them the task. So threads in Python are really fast. You can start a thread in like nanoseconds. Whereas if you look at multiprocessing, so to start a Python process actually takes a lot of time. So it doesn't make sense to launch a Python process if that process is only doing some work which takes like 10 milliseconds. So threads can run in parallel. The startup time is small. You can exchange data freely between threads. Coroutines are concurrent. They're not parallel. They have the smallest startup time out of all of these models. And again, you can exchange data freely between coroutines in the main process. And both of those are great for small I/O-bound tasks, so tasks which are using like the network or disk or reading and writing from databases that don't require multiple CPU cores. And then when we look at like truly parallel stuff in Python, we've got multiprocessing, which is you basically launch multiple Python processes and then you just communicate between them. And you've got subinterpreters, which is a new one, which I'll talk about. So if we took this problem in Python, we've got an array of 100,000 integers, and we wanted to calculate for each item the distance to 50. So that takes a fixed amount of time, depending on how busy the CPU is. If I split that up and used threading, that's why I put this asterisk on the previous slide, and launched multiple threads and gave each thread not 100,000, but like a piece of that. Let's say we'd launched 2 threads and gave each one 50,000 numbers. Would that be faster or slower? Anyone for faster? Put your hand up. Okay, nobody. Cool, you're all pretty experienced at this. So Python has a GIL, so even though you've got 2 threads running at the same time, only one of them can actually execute tasks. So even you would kind of expect it. If you chunk this up in other languages, you would expect that if you launch multiple threads, you could split a problem like that into multiple CPU cores, and they could run freely and execute in less time. So in, oops, what happened there? All right, so let's look at the GIL. Okay, so the lock in Python 3.11, it's called the global interpreter lock, but it really belongs to the Python process. This lock makes sure that only one thread can execute at any time in Python. In 3.12, there's a new feature called Subinterpreters, where you can launch an additional interpreter which has its own lock. So this means that you can have essentially they're like mini Python processes. That's probably my analogy with subinterpreters. And they each have their own lock, and you can split tasks, and they can run truly in parallel. This is quite a big difference. So if we looked at, if yellow means they're executing, in 3.11, if you spawn 2 threads, only one of those threads can run at any one time. Whereas in 3.12, you can launch multiple interpreters, subinterpreters they're called, and each of those subinterpreters can launch threads. And then if you do that, then you can have more than one thread running at any time. So if we look at that and we take a problem, which is calculating pi to 200 decimal places or 2,000 decimal places, I've picked those numbers because I'd say that's like a small workload and a slightly bigger workload. They're both computationally expensive. So if you looked at threads, for example, so if you did so that's the time it takes with threading. If you use subinterpreters, then it is a faster time for 2,000 decimal places because it's got I use this with 4, sorry. So if you had 4 threads running with a single interpreter, a single process, it's slow. If you use subinterpreters, you can calculate pi quicker because you've got 4 potentially running on 4 CPU cores at any time. If you use multiprocessing, then just calculating 1 is slower because it takes time to actually spin up the process. And then the overall time ends up being slower. So what you can do with subinterpreters is if you have a piece of work to be done, you can run that concurrently and in parallel, which is effectively a better model than multi-threading in the old Python. So we'll go on to no-GIL in a minute. So my quick conclusion is that subinterpreters are like multiprocessing with less overhead and shared memory. I think that going forwards, the subinterpreter model makes a lot more sense than multiprocessing, and in the future, we will stop using multiprocessing altogether because there are so many issues with having to pickle data and transferring data between Python processes, and subinterpreters have got a much better way of doing that, which I'll demo in this talk. Okay, so that's a recap on topics that I've covered previously. If you want to watch the talk that goes into more detail on subinterpreters, I did that last year at PyCon APAC. But considering the free threading and no-GIL is the hot topic, I want to address that and talk about it, and then compare the two approaches and see really which one could be successful going forwards. So free threading. So from Python 3.13, you can disable the GIL. So earlier on, I said that with Python, even if you've got multiple threads, only one of them can run at any one time because there's a lock which belongs in the interpreter. In 3.13, you can effectively disable this. You need to install a special version of Python to even get this feature. It's highly experimental. If you're installing from Windows, it's actually an optional feature. If you use the macOS installer, it's an optional feature when you go through the installer process. If you're using Linux, you have to compile CPython from source and provide some extra flags when you're compiling from source. So it's hard to find, but the feature does exist. And the reason it's hard to find at the moment is because the developers want people to test it, and they mainly want package maintainers to test it, and then users to have a look at and experiment with this feature. So Python 3.13 single-threaded code will be faster anyway because of other optimizations that have nothing to do with this project. So when you're using Python 3.13, you will probably find that your code runs faster regardless of what's happening with free threading because there are optimizations, some of which were actually mentioned in the room before this talk. And it's always important to remember that the GIL exists for thread safety. The whole point of the GIL is that when you're working in Python, on the C level, it uses a reference count and a garbage collector. The Python objects have a reference count attached to them. That counter is not and was never designed to be thread safe. So it's possible that if you had 2 threads running, one of them reduced the reference count, and the other one didn't realize because it hasn't checked since that happened. It tries to read the object. The object no longer exists, and it's basically trying to read from memory, which has been deallocated, and that's where you get segmentation faults or undefined behavior. So the GIL exists as a way of making thread-safe Python code really simple by making sure that only one thread can run at a time. It's also important to note that free threading introduces a new ABI, the application binary interface. What this means for most people is that you need special wheels for this to be supported. So if you're using a package from PyPI, that package needs to either have wheels for free threading, or it needs to have a source distribution, or it needs to be in pure Python. You'll find that a lot of packages are not supported, or if they are supported, you need to compile from source. Cool. So what this looks like in 3.13 is that where previously we had a GIL which was attached to each interpreter in 3.12, if you're running this special free-threaded mode of 3.13, you can have two threads in a single interpreter that are running simultaneously in parallel. I've also included some tiny locks because whilst the GIL is removed with this free threading mode, there are other locks. You can't just get rid of them altogether. You still need to have some sort of thread safety. So there is also that to consider. So to do this, you might be wondering, how do they get rid of the GIL? Because it's been there for so long. There were basically 3 steps. 1 was remove the GIL. 2, change the memory allocator and the garbage collector because they weren't thread safe. And then the last thing is fix all the C code that assumed that the GIL existed. We're basically still working on this part. And this is going to take a long time. So we're basically at the beginning of this journey of making like truly parallel Python without people who are using it have to worry too much about how it's working on the C level. There's also another challenge, which is that in Python, a lot of the extensions that you install, other packages you install, are written in C. And they were written in a way that assumed that the GIL was there. So because the GIL was part of Python, you didn't necessarily have to worry about thread safety. Now, if you then take the GIL away, then you've got all these C extensions which just kind of assumed that the GIL was there to deal with thread safety, and they didn't put any kind of locking or thread safety in the C code. So I say this is going to take a long time because the behaviors we'll start to see more of is with packages which either haven't tested this or you haven't tested all the edge cases. Then we're going to have all sorts of issues with threading. I've seen some package maintainers say, OK, great, we support free threading because we ran the test suite and it passed. The challenge with this is that you run the test suite in a single thread. So it's like, OK, yeah, our code works with free threading, but you've only tested it in a single thread and in a sequential order. So it's going to be up to the users to discover all these issues when you try and run things in a multi-threaded environment. So yeah, good luck with that. So is it any faster? So everyone's been talking about this GIL thing for like almost 2 decades now, and everything's going to be so quick when it gets taken away. So if we go back to the benchmark, previously running it in multiple threads wasn't any quicker because the GIL existed. So now threads is a quicker approach. If you compare it with subinterpreters, subinterpreters would be slightly slower because it takes a bit of time to spin one up. And then multiprocessing is the slowest approach. So effectively splitting a problem like calculating pi to however many decimal places, doing that with multiple threads with the GIL turned off would be really fast and effective. Hold on a second. That's great, but that's theory. Does anyone here calculate pi to 2,000 decimal places on a regular basis? No, because it's a nonsense problem. It's great to demonstrate like how threading can work and the benefits of threading, but it's not realistic. It makes a cool benchmark, and you can get some interesting graphs that say, hey, look, it's 4 times faster when you've got 4 CPU cores. But real programs don't work like that. So what I wanted to do and talk about for the rest of this session is some real code and actually trying to look at web applications in particular, because I think they pose an interesting problem. So if you pick a typical web application, it is both a parallelism challenge and a concurrency challenge. Because with a web application, a web server like Django, Fast API, Flask, if you've got 8 CPU cores on the server, hopefully more than that, you'd want as many of those CPU cores to be working on delivering responses back to people who are making requests to the website. So you want those to be able to work effectively in parallel. You've then got, typically, you're reading from disk, or you're reading or writing over the network, or you're reading or writing to a database. Those are concurrency type problems because you're waiting on something to finish in order to continue executing. So I think web applications are an interesting problem with both subinterpreters and free threading, because it's interesting to see, would we get any real benefit in disabling the GIL in Django, for example? Like, would that make any real difference? And what role would subinterpreters play in an application like that? Because at the moment, when you look at the architecture, how most people deliver this is they do something called multi-worker, multi-thread. This model is used in GUnicorn or Uvicorn. Actually, Uvicorn's slightly different. We'll get onto that. So what you do with GUnicorn is you spin up, let's say you've got 8 CPU cores, you spin up 8 Python processes, and each one has a thread pool. And then they share a socket, and they can listen to requests coming in, and they can execute and respond to those requests. This is how most web applications run in Python today. It's quite effective, and you've effectively got around the GIL problem by spinning up multiple Python processes. So each one has its own GIL. You've got 8 processes, 8 workers, and you've got 8 CPU cores. So does the GIL really matter? Because, you know, you've got 1 each, 1 per CPU. Kind of does matter because not everything is truly concurrent. So the GIL doesn't always get released when you talk to the database or the network. But this model has worked and served us pretty well. So the first thing I wanted to try was, can we do multi-interpreter, multi-thread? So can we just get rid of multi-processing altogether and replace that with subinterpreters? And if we can we also introduce some shared memory so that, because one of the big benefits of subinterpreters is that because they run in the same process, they can actually access the same memory. So you can have an object, or a cache is the demo that I want to show you, which is spawned by one and can be read by others. So let's have a look at that. Do you want me to make it a bit bigger, or is that okay? That's okay? Cool. So what I've effectively put together is a small web server that spins up, instead of GUnicorn, which spins up processes, Python processes, it spins up interpreters. So it's the same kind of idea. You use subinterpreters instead of processes. And let's have a look. So a subinterpreter I've designed as a worker. What is confusing with subinterpreters is when you launch and run code in a subinterpreter, that's a blocking operation. So you often want to create a thread and then run the subinterpreter from the thread. That confuses people because they're like, why am I making a thread? But you want to make it non-blocking, otherwise, what's the point? So how you normally deal with subinterpreters is you would create a thread. Easiest way to make threads in Python is to make a class that inherits from thread and then implement the run method. So what I do here is basically make a web server, it listens on a socket, and it runs some code. That code launches an ASCII or a WSGI application. And I've then got some custom code to listen for like me pressing Control-C to shut down the web application. And then it talks to the subinterpreters and tells them to close. So it's not too much code. This is basically a extension to Hypercorn is the ASCII wrapper that I'm using under the scenes here, but I think that in the future, other web frameworks will build something like this and ship it. And then I've got a function which will say how many workers do you want, and then spin up that number of workers. And then I've just got some boilerplate code at the bottom to take arguments like what's the application you want to run and where does it go. So that is how we do spin up a subinterpreter. We do interpreters.runString, and we give it some code to run, and it runs that in a subinterpreter. The worker itself, so this is the code that runs in the subinterpreter, basically just launches the web application, and then it listens for a kill signal, and if it receives a kill signal, it shuts itself down. So all I'm doing is launching a hypercorn, and then running the ASCII application. So what I can do is, I just had it running before, I can run my script, and I've got 8 CPU cores on my machine, so it's going to spin up 8 subinterpreters, and each one of those is going to listen on a shared socket. We use a socket dupe command to do that, and then I've written like a custom bit of code for the logging interface so that it prints the subinterpreter number before the log statement, just so you can see which one it is. It's a bit small. Okay. It makes it bigger. Cool. Okay. So I don't know. Let's do. So if I just run Apache Bench concurrency of 10 and 1,000 requests, then you'll see in the background all the different subinterpreters, which is this number here, responding to the requests. So effectively, we've replaced multi-worker, multi-thread with subinterpreters. Now, that's an interesting solution. Where I think it gets more interesting is for my Flask application, I wanted to do something a bit more complicated. So I've got so I got my Flask application, which is being served in this environment, and in there I've calculated like a list of dummy users and populated those. Because I've got 8 subinterpreters, I want to cache that information. And this is something you would do in Django a lot, is you would cache things in memory, whether that is like an object cache or a shared object cache. With multi-processing, you can't easily share the cache in memory between the processes. So people typically introduce something like Redis, possibly like as another service layer where you've got a cache, which can then be read and written to from each of the workers. With subinterpreters, because you can access the same bit of memory, what you can do is you can basically introduce a dictionary, which is a cache, and then all of the subinterpreters can access that dictionary and read and write from the same cache pool. This is an interesting solution, I think, because you get a benefit that you can't do from multiprocessing. So what I've done with the worker is I've introduced a shared cache, and I've just got an implementation called interpreter cache, and I use a communication channel between the subinterpreters to request a cache entry from a key. If it gets a hit, so if it exists in the cache, it gives you back a memory view, which is basically a way of accessing a piece of memory in Python. And then you can read from the memory view with 0 copies. So the different interpreters in Python can actually read from the same bit of memory and access the cache without having to copy data or transfer over a communication channel. This effectively eliminates having to introduce something like Redis and having to have the extra network hop to get stuff in and out of the cache. I think it's an interesting solution. This demo I've also done with the guild disabled. So when we did the list of users, it was actually spinning up a thread pool. So what we're doing here is we're doing no guild subinterpreters, which means that even though I have 8 subinterpreters, each one of those can spin up as many threads as it like, and each of those can also run in parallel. So the parallelism options with this kind of model are pretty limitless. And if you're working with a server which has got, this is just my local dev box, but my remote dev box has got 64 cores. So like if I'm working in an environment like that, I can actually push each of those 64 cores to the absolute limit. and the parallelism option on that is massive. So the reason I think you could do that, and I'll go back to my slides. Okay, so in that model, we've got multiple interpreters, we've got shared memory, we've got a cache worker with a database, and we have a local copy, and each one of the threads can request information out of a shared cache. That is a shared piece of memory, so it's not copying or transferring bits over even a local network. It's just giving you back effectively a pointer to that memory space. With one worker multi-thread, then we can effectively have lots of threads running. The approach I think makes more sense for web apps in particular is to do multiple interpreters, and each one of those interpreters also has the GIL disabled, because I've talked about threading and multi-threading, but who's using Fast API? Okay, a few of you, anyone using Quart or any other async ones? Okay, so they use coroutines, so they don't spawn threads anyway. Disabling the GIL is great if you're using multi-threading, but with async, coroutines are not threads. There is a async loop that runs in the interpreter, and what I think actually makes more sense is that each interpreter has its own async loop. And yes, threads can run concurrently, but if your application is fully async, you're not spawning up threads anyway. So if you've got multiple interpreters running, each one is running async. Each of those coroutines can run in parallel. Just disabling the GIL doesn't necessarily give you that, because you're still running everything in a single thread, unless you've explicitly spawned a thread outside of that. If you're using something like Unicorn, everything is running in a single process in a single thread. So it's running with an async loop. It's not using multi-threading. So I've seen people complain. They said, oh, I disabled the GIL. My Fast API is still the same speed. It's like, yes, because it's all running in a single thread. It's not suddenly going to become parallel. So my closing thoughts are sub-interpreters or free-threading. I think the future actually could be both. Sub-interpreters make sense, I think, for async in particular, because you can have multiple workers. For async I/O, they are not threads. The coroutines are not threads. So this problem basically introduces an opportunity to have parallelism where we didn't necessarily have it. Removing the GIL on the interpreter level is the first step. Getting all of the libraries to behave and work well without the thread lock or any kind of thread safety is going to take a lot of time. And it's going to introduce a lot of really weird issues and bugs over the next few years. And also, the winning solution is not always the best one. It's going to be whichever one is the most convenient. So as to whether sub-interpreters or free threading is going to be the winner, I don't know if there's going to be a winner out of this. I think the future is actually a combination of both. And want to conclude on a few points. So I think multiprocessing will go away. Sub-interpreters makes a lot more sense, less overhead. You've got the shared memory idea, which is a lot more effective than pickling data and transferring it over sockets. Free threading will be a better solution for thread pooling and data exchange, which isn't necessarily a web application problem. It's used in other spaces as well. The Python ecosystem relied on the GIL for thread safety. Taking that away is going to break things in really unpredictable ways for a long time to come. And my second point, there are terms and conditions to this. I gave a version of this talk at PyCon US, and actually just to show you how much progress we've made, everything in the PyCon US talk, which has since been solved, that was in May, I've crossed out because there were a lot of issues in May in release candidate 1 of 3.13 that have been fixed in the last 2 months. Even some of the stuff I just demoed to you was not possible like 2 months ago. So just to show you how quickly this stuff is moving, I've included those and crossed them out. But yeah, there are still definitely some limitations. And if you missed the QR code at the beginning, it's available at the top right-hand corner. And I'd love to answer any questions.
Yeah, thank you so much, Anthony. We are right on time. So, anybody have any questions to Anthony?
Thanks. How would you suggest a package maintainer to test like this multi-threading or no-guild stuff in a continuous integrations environment? Because you are saying we are mostly just testing in a single thread that's not useful. And also a question not related to this talk, what is the Q stuff on your left corner? Yep.
Oh, I'll answer the second question first. That's easy. VS Code Pets is my extension, and yeah, it's available. The first point, what would I recommend to package maintainers who want to try and test whether their code potentially is thread safe or might have issues with the guild disabled? First step is just run your normal test suite with the guild turned off. That I think ticks a box that it is compatible at an ABI level. The next thing I would probably do is to introduce one of the repeat extensions. If it's PyTest, there are repeat extensions for PyTest, and then using like the XDIS to run those in parallel. The problem with XDIS is it normally spawns up additional processes to do it. I would love somebody to solve this. For Subinterpreters, I wrote a custom test runner to run the CPython test suite in parallel and actually repeat the tests, and that uncovered a whole bunch of issues. Because originally they were like, oh, the test suite passed, and it's the same problem. It's like, yes, but you ran it in a single thread in a single process. So I would love somebody to write a PyTest extension that basically does parallelism and repeating, because race conditions are really difficult to find. And even if you get that to work, you're still probably going to get issues from your users. So as a first step, I would look at repeating tests and running them in parallel with whichever PyTest extension does that without spawning up processes.
Hi, my old knowledge about the standard library. They are not all thread safe. Is it true or solves this problem?
That's true. Not all of the standard library is thread safe. There are actually one of the items which is crossed out because it's been fixed since May was that the datetime module was not thread safe.
Yeah.
Yeah, which. Yeah, so, yeah, exactly. So there are still lots of issues to be found. Yeah, I agree with you completely. Any other questions?
For the interest of time, we'll take all the questions offline. Anthony will be around. You can meet him in the hallway or at the outside of the this room. Thank you so much once again, Anthony, for delivering your insightful thoughts on sub-interpreters and a lot of threading things. We can hear all the day, but for the interest of time, we had to stop here. Thank you so much. Give Anthony a big round of applause.